Alright guys, so in this video we want to do consolidation testing on a clay specimen. Alright, so the equipment that we need for this test is obviously the components of the actual consolidometer, which are shown right here. So this would go on top. I'll show you how to assemble that in a minute. This is the consolidation ring, or the sample ring right here. What you want to do with this is first, before anything, just measure the height and the diameter of this to know the dimensions of this so you can calculate volume later on. This is the trimming tool that I'll place the ring inside, and with the help of that I'll be trimming my clay specimen. This is the clay specimen. It's all wrapped up to maintain its moisture content. So I'll open that up and take a initial moisture content in a minute. I have filter papers for the top and the bottom of the specimen, and these are other components. This is top and the bottom porous stones. I'm actually going to saturate these in just some water, keep them in there for the time being while I'm preparing my specimen. This is the top cap that will get placed on top of the specimen whenever it's ready. I'll show you that in a second. This is a plate that I'm going to use for placing my specimen for trimming. Obviously a caliper to make any measurements that are needed for this test. So I'm going to open up the clay. Again, some kaolinite clay that looks like this. I'm going to place it on my rack, or my little plate, and what I'm going to do is place the specimen ring on top of that clay sample. The next step is to place this on top of it. And the reason for having something like this on top is that you want to bring the clay up to a higher level than the height of the specimen ring, and this will help you do that, right? So this is the specimen ring, and it's only that much, but this, when this goes on top, it's a little bit taller, so you can bring the clay higher and chop off the top and trim that. So I have that and this on top. The next step is to push the specimen ring, or the sample ring, inside the clay layer with a loading device like this, and by applying a little bit of pressure. So that's what I'm going to do. This thing has a little jack that is going to help me push the trimming device into the clay layer. I only do a tiny bit, maybe just a couple of millimeters. I'll push it in. And once I push in a little bit, then I'm going to release the jack and remove it. Right now I have some of the clay inside the specimen ring, or the ring generally. Hopefully you can see it. I don't know if the lighting is great, but you have some sample in the ring, right? So if I had pulled that out, you see that I've pushed that a little bit inside. What I'm going to do from now is I'm going to trim the sides of this using my wire saw. And the motion that I'll be wanting to do for this is to go in a little bit and go outside. So something like that. I don't want to cut vertical. I want to do something like this. and chop off the excess material. As best you can. So something like this. Then you would want to take off anything that's very close to the ring, but going away from the ring, not going underneath it exactly. Just want to so this is the first part. I place it back on and push a little bit more the ring inside the specimen. Careful not to do it too fast or overdo it generally. Maybe just a couple of millimeters of soil in there, and then repeat the process of trimming a few more times until you bring up the clay all the way. So I got a little bit of more clay now in there. Still haven't reached to the top of the ring. So I'm going to continue this for another couple of times. Getting closer to the middle of this clay sample that we've given you, and you're getting closer to the stuff that you're actually measuring. That's when you want to also collect a water content sample out of this to know the initial water content, which you can translate to void ratio and get your initial void ratio from. So again, close it up. And repeat the same process. So now we have a little bit of more clay in here. It's almost to the top now, the top of the specimen ring. I'm going to trim off the excess, and we should probably be able to get our sample done by doing this one more time. Probably just chop this off also, I don't need it really. There we go. Almost trimmed. This is what the trim looks like from the sides. Okay. So I'll do this one more time. Push some more soil in. You can see now that I have soil now that's now raised above the specimen ring. So I can cut this top off and use somewhere in that middle area for my water content measurement. So here's what I'm going to do next. I'm going to still keep this on top. I'm going to trim all the sides off. I'm doing it a little bit more quicker now that I have the clay in there. So this is what this looks like. I'm going to flip it over, keep that bottom trimming ring still in there. I'm going to chop off the top. I'm first going to get all the excess stuff on the sides, and then you don't want to cut too much because sometimes that can cause some problems. So then I'm going to go down like this and cut sideways. Grab that. So now essentially we have a trimmed specimen. Now is the time to try to remove all the excess soil from the side of this ring, because you're going to reweigh this, but you want to make sure that you're not having any material on the side of the ring. So I'll just use my hand to take some of it off that's stuck to it. And after that, what you want to do is, first of all, grab some of this stuff that were just immediately above this. So maybe this, you can grab some of this for a moisture content measurement in a can, or a evaporating dish that you can use. I've done that before. So here, maybe I'll just grab that and use that piece for the moisture content / initial void ratio. That'll also help you calculate the saturation by knowing the mass and the volume of your specimen. So you'll know initial saturation and how much that would be. And obviously by either assuming or knowing the GS of the soil or the specific gravity, you can make your other calculations. So right now I'm just making a nice flat surface on top of the clay. I already know the diameter because I've already measured it. So this is what I have right now. That's the close-up view. So all nice and flat at the top. Also going to try to clean up anything that I have on the sides of the ring, because I have to measure the mass of this, and I want the mass to be as accurate as possible. So then I flip this over, and the last step is to cut that excess portion on the top of the specimen. So again, I'll go through the middle and go sideways. So that's one, and then here's the other one, and then the rest is just to make it smooth and flat at the top. Pretty much gotten everything off of this, so this is our final sample. This is the top view and this is the bottom, so all nice and clean. This is where I would measure the mass to know exactly how much I have in here. And the next step is to actually place it in the consolidometer. So the next steps are actually to place this bottom porous stone here and place that wet filter paper on the bottom. So we have that. Then what I'll do next is actually place my specimen here. With another filter paper on top. And the top porous stone going on like that, facing this way so that I can place that this piece on top of it. I'll do that in a minute. This is the last part that goes on, and I'm going to screw them all up here. and make it tight. And the last step after this would be to add water and keep this saturated. And so that's the last piece. And place this on the loading device, which I'll show you in a second. So in practice, adding the water is done at different stages of the test. So sometimes what practitioners like to do is place the sample in the loading device and apply the first maybe load step, then add the water. And the reason for that is, once you add water, if you added water right now, water would get into the specimen and actually tend to expand a little bit. But if you did that after maybe the first step of loading, the tendency for that expansion, if you added water, would be less. So what we'll do is, first run the first load step, and then after that's done, we would add the water and basically submerge this area with water, and then add the other loading steps. So in the next part, I'll show you how to assemble this on the loading device and how to run the consolidation software and record the data. Right, guys, so we have a consolidation table with two loading devices, basically. We're going to be using this one, and we also have a little power tool here that is going to help us take measurements with this LVDT. This LVDT is something that is going to take digital measurements for the vertical displacement, or the vertical dial, basically. So you can see that this can extend or get compressed, and essentially what the LVDT is going to give us is voltage. So we're going to record the voltage, but we're using a calibration factor to translate the voltage into basically displacement, or the deformation of the specimen in millimeters. So having known the calibration factor for the LVDT, we'll be using that factor in the consolidation software. This voltage is usually set to 10 volts. So the next step, which I'm going to show you with a close-up, is to assemble the sample that we prepared in the loading device. But to show you from a zoomed out point of view, this is what it would look like. So I would want to put this sample here, place this basic rod on top of the specimen, and then I would apply the loads on this portion. I'm not doing that right now because I wanted to show you something before I did that. Now, as you can see, there is a arm with this view. So there's an arm that applies the load to the specimen. Now, if I wanted to, I could remove this loading area to one or two other positions. So this loading device has 3 positions that I can apply the load to. The first one is 9 times, the second one is 10 times, and the last one is 11 times. So essentially what that means is, with this moment arm, what you're doing is you're factoring the load that's being applied to this location 10 times higher with this arm to the specimen right there, right? So for example, if you had applied 1 kilo of load at this point, the sample is feeling 10 kilo of force on it, right? So, which also translates to pressure. So whatever pressure you're applying here, 10 times that will be applied on the specimen, okay? So guys, in order to screw this part on top of the specimen, right now there's no contact between this screw that I have here in the top of the specimen. So if I added any load right here, nothing would get transferred. So what I'm going to do is I'm actually going to hold this part upright so it doesn't make any adjustments very, very easily. Just hold it right here. Yeah, not too much. And then what I'm going to do is I'm going to screw this all the way in. Have it all in place and ready, and then we're going to start the consolidation software so you can see it. So once I get close to it, I'm not going to screw it in too tight. But the next step is to get the LVDT in place. So this is what that would look like. So I would screw that piece in and then extend my LVDT to some level. So this is what that would look like, and then I'm going to screw it in, and that's its final position, right? So now it's resting on top of this rod, and as the sample is consolidating, the LVDT, or this will be moving downwards, and with that, this portion of the LVDT will be moving, and that is what will translate into displacement later on. Okay, so right now no loading. I just want to now show what the consolidation software is going to look like. I'm going to open it up. So this is what the consolidation software looks like, guys. We have two plots. One is the dial reading versus time in log scale for the Casa Grande method. The other one is the dial reading versus square root of time for the Taylor method. You'll be using both of those for processing the consolidation data. We have two other things here at the top. One is the channel where the data is being recorded. So I'm going to go to channel 1 since that's what the current configuration is. And I also have a calibration factor that I need to apply here. And basically what this is, you can see the units, they're millimeters per volts. So what this would do is translate the voltage that's coming out to millimeters. And so this is the page for the calibration of the LVDT, and what we have done is we measured the voltage versus displacement using a caliper, and this same LVDT that we're using for the consolidation test. Same concept as the other types of calibrations that we've done, except that those were for loads and this is for displacement. So we regress the data, and your calibration factor is 3.197, basically the slope of this line. So 3.197 is the calibration factor that we'll use here, 3.197, and the units again are millimeters per volts. So this value multiplied by voltage will give you millimeters. Okay, so the next step is to create a folder and a file with a name for the load step, and once we've done that, then we're ready to add the load to the consolidometer. So what I'll do here is I'll press this button, and it'll ask me to designate a location for this. So what I'll do is first I'll create a new folder and call it CEE 128L consolidation. Then obviously each group would need to have a certain folder for themselves. So group X, and then the first file name is, I'm going to call it stage 1, right? So stage 1, and we know that the applied pressure is going to be 50 kPa, right? And I'm going to press OK, and you see that no data is being recorded yet. So what's going to happen now is the measurements or the readings are going to start once we have applied a load to the system, which we haven't yet, right? So this is the next step that we will do. I'm going to apply the load, and what I'm trying to do right now is try to get both of these in one shot for you guys to show you the loading, and at the same time it'll start recording the data, and that's what I would want you to do. Ideally, the way you would want to do this is before pressing OK on that screen in the computer, you would want the person who is going to apply the load to be ready. So what you would want to do is have that person be in their place, ready to apply the load, and then one person ready to press OK, and then once you do that, then the computer is going to start its measurement. So let's look and see how that happens. There you go. So I applied the load very, very slowly, and you can see how the two plots are being generated in real time. So on the left-hand side, again, you have the Casa Grande method. On the right-hand side, you have the Taylor method. Let's actually try to also show this with the bigger monitor to see if that's a better view. Alright, so now that the first load step has finished, what I'm going to do is I'm going to inundate or add the water and submerge the specimen with water, keep it saturated, and I'm going to do and show you the second load step. So I'm going to add some water here around the area that's all dry right now. Should have actually just stopped the data recording using the stop button and then do this. So there we go. I've submerged the sample. And now is the time to create the next stage file. So I'm going to go here and create the next load step, stage 2. And we're going to 100 kPa. So I'm going to grab the load. And by the way, this I'm going to use a 1 kilogram load. Each 1 kilogram of load will translate into 50 kPa of load, or 50 kPa of pressure on the specimen. Right, so right now I already have 50 kPa, so I'm going to add one more that'll make it 100 kPa, and at the same time I'm going to have my assistant press the OK button at the time that I'm going to count to 3. So 1, 2, and 3. So you'll see that the new plot is being generated, and the data is being recorded in real time. We'll continue this until the second load step is finished, and when you can actually see that kind of curve on the consolidation plot that kind of follows the backward S, or following my hands right here, once you get that shape, that is the time where you know a load step is finished and you can move on to the next loading or unloading So now with this backwards S shape kind of curve, I'm going to let it stay for a little bit longer, but what you could see right now is from this plot and drawing the two tangents here, you can interpolate the time to primary consolidation. That's the main use for the Casagrande curve, as well as the 0 reading and the 100% reading and the time to 0 and 100%, as well as the T50 of the specimen. From the Taylor method, you'll be able to get the T90, or the time to reach 90% consolidation. So then once these steps are done, you can go and move to the next load or unloading stage. One thing to remember is once all the loading stages are done and you're taking out your specimen, you would want to take a end of the test moisture content to know what the void ratio of the specimen is at the end of the test, and to compare it with the initial moisture content or initial void ratio that helped you calculate and reach the final void ratio, and compare the two values of the final void ratios with each other.